Ladies and gentlemen, esteemed colleagues, welcome to today's webinar on deep reinforcement learning, a modern approach to adaptive optimal control. And it is my pleasure to open this session on behalf of UNIDO. This session marks a significant step forward in our journey towards integrating cutting-edge technologies, advanced technologies in our industries, but also educational frameworks. And today, we are privileged to have with us Professor Milan Rapajic from the Faculty of Technical Sciences, Novi Sad. Professor Rapajic brings an extensive background in decision and control theory, optimization, and intangible intelligence systems. His work spans numerous projects that bridge the gap between commercial application and academic theory. He will lead the session today. From us, from UNIDO, today's webinar is the foundational webinar for the series leading up to the establishment of the Smart Manufacturing Innovation Center with the support from the government of Slovenia and Slovenian Enterprise Fund. And here we are proud to collaborate with the University of Novi Sad. I'd say that this session is not just a lecture, but I'd say it's a glimpse into what SMIC will deliver and into the future of manufacturing control systems that you, and I assume we have a number of students from the University of Novi Sad, could soon be leading. But of course, the significance of this webinar extends beyond just today's learning. It's a precursor to the regional conference and inauguration of the Smart Manufacturing Innovation Center in Novi Sad next month. This event will be a cornerstone for future collaborations, innovation, and education amongst the brightest minds and industry leaders that we are going to be meeting at the launching event. The whole initiative underscores UNIDO's commitment to fostering robust innovation ecosystem in the Western Balkans, in Serbia, at the same time aligning with the EU standards and technological advancements. What I would like you to encourage, regardless of who you are, researchers, practitioners, students, decision makers, or the representatives from international institutions here today at this call, is to engage actively, and my colleagues will guide you on how to do that. Ask questions, share insights, and explore how these technologies can be adapted to your fields of work and study, or to your coursework that you are now doing under the guidance of Professor Jelecic and Professor Rapajic. Your participation today is crucial for shaping the future where technology and innovation drive our regional growth and integration into the global economy, which is one of the most important aims of us as a United Nations organization. I would like for this session today to become a stepping stone towards the official launching of the SMIC and the June's events. And I would like to encourage you to provide your insights and the interactions from today, which we will collect, and they will contribute to our discussions and collaboration in the upcoming conference. I'd say that this is an opportunity to be at the forefront of Industry 4.0 for the Western Balkans. Thank you very much for joining us. On behalf of UNIDO, I welcome you to this initial webinar, and I would like to give the floor to Professor Zoran Jelecic with the opening remarks from the SMIC.
Thank you, Alexei. Thank you, Alexei. I will be very short. Dear friends and colleagues, it's a great professional honor and personal pleasure to greet you in the name of Smart Manufacturing Innovation Center. As you have heard, this research educational hub will be founded next month in Novi Sad, And prior to formal opening of the center, we'll be hosting a series of webinars covering center focus areas like artificial intelligence, digital twins, automation, control system, power electronics, embedded system, hardware modeling, and simulation. For our first speaker, we chose my dear friend and very highly respected professor, Milan Rapajic from University of Novi Sad, and he is also visiting professor at University of Bordeaux. He is very active, as you can hear, in designing, developing, commissioning sophisticated control and machine learning algorithms in engineering practice. But actually, what is even more impressive than his professional scientific engineering contribution is his dedication to the teaching profession. And you will have opportunity to learn more about this and his dedication to the professor in next 45 minutes. Please, after these 45 minutes, we'll have 15 minutes for the questions. But if you don't have option to ask question or something like that, please type it in question and answers. I will respond to all the questions in following days, and you will have video materials and Q&As both of our website and link from this lecture. So please enjoy the lecture with Professor Milan Rapajic. I'm sure you will do. Okay, have a nice day.
Thank you. First, let me say thank you to everybody who are attending. Thank you, Professor Jelicic. Thank you, Mr. Savrasov, for introducing me. I also want to thank UNIDO and SMIC for giving me the opportunity to present this lecture. It will be, I hope, relatively short, but deeply personal view on a field that is on a topic that is modern and interesting in the last period, but which actually has a pretty long history behind it. So first, let me share the screen. Just a moment. I hope that you see the presentation. It's the first time that something can go wrong. Is it visible?
It is visible, but not in a view mode. It is in your mode. So you can probably to start to start presenting.
I did start presenting.
No, slideshow.
It's a slideshow is starting. It started. Maybe there is a delay.
It's a small delay.
Yeah.
We wait a little.
Just let me end the slideshow, start it again, maybe. So I ended. I started again. Better?
Still the same.
Same.
Try to share another window, the window of the slideshow.
Yeah, that's fine.
One,
Perfect.
Yeah, maybe I can do it like this. Stop sharing. And then I share this. Now you should see an empty screen from me, I guess.
Yes. Okay.
Do you see it now?
Perfect. Don't change anything.
Oh, thanks. Okay. So the topic of the talk is actually reinforcement learning, or deep reinforcement learning, if you like, but from a slightly different perspective than this is usually covered. I want to cover this as a modern approach to something that is known in control community as adaptive optimal control, in essence. So let's start by actually defining what I'm going to talk about. So reinforcement learning is just a framework for solving sequential decision-making problems in uncertain environments. So what does it mean that a decision problem is sequential? It means that I will suffer the consequences of action that I take. So the action that I take today may return to haunt me tomorrow or the next day. And the fact that the environment is uncertain actually means that it's not quite clear to me at this point what are the consequences of those actions actually. So the problem seems difficult, but if you look at it more closely, you may see that most real-world problems of decision-making are actually fitting perfectly into this framework. So just from a short historical perspective, the decision-making problems actually have a source in three completely separate fields of research that came together somewhere about the 1980s. And when they become the reinforcement learning as we know it today. The first field is related to psychology and behavior studies, mostly studying of behavior of animals, giving rewards and expected favorable outcomes, giving penalties or punishment and expecting suppressing behavior. It is the line of study that was particularly interesting in the beginning of the 20th century, but it has evolved since then. Another field or another branch that brought us reinforcement learning is maybe even more surprising. It started with analytical mechanics with Hamilton and Jacobi in the mid-19th century, but actually then it became more interesting with Bellman in the middle of the 20th century, and also Kalman, Howard, and other people who defined actually optimal control and dynamic game theory. And finally, the third line is related to bootstrapping and so-called secondary reinforcement. Bootstrapping is a set of techniques that actually uses estimates to build other estimates. It has links to both computer science and behavioral studies, but it became one of the cornerstones of modern implementations of reinforcement learning, although it started with Minsky, who is one of the fathers of artificial intelligence again in the middle of the 20th century. I will not deal with the historical development of reinforcement learning today because the talk is too short, obviously. I just wanted to highlight some sources that are actually quite surprising if you never thought about the origin of the reinforcement learning in particular. What is historically interesting is the year 2016. It is probably the year when reinforcement learning lived to see its breakthrough, but I would say that maybe entire artificial intelligence field actually got a boost. In this year, software called AlphaGo, which was developed by a London company based in London called DeepMind, which was eventually bought by Google, managed to defeat this very famous Go player, Lee Sedol. This is the gentleman in the upper image. The three other gentlemen are the people who were responsible for creating AlphaGo. The leftmost gentleman is actually the co-founder and director of DeepMind, and the middle one is the chief architect of AlphaGo. What is so important in this year 2016 is the sheer complexity of the Go game and the problem that is being solved. Because the computer AlphaGo managed to beat Lee Sedol in 5 consecutive games. The score was 4-1. Computer won 4 times, and Mr. Sedol won only 1 game. In order to win this 1 game, Lee Sedol had to play something that was never seen in a Go game before. He essentially had to invent a new strategy. And this game was later praised by many of professional Go players as one of the master classes in the field. Yet Lee Sedol, after this loss, was quite pessimistic. He was really stressed, and if you have time, it's really interesting to read his interview after. He was very pessimistic about the future of mankind and about the capabilities of humans with respect to machines. What is so interesting here is that Go is the most complex game ever imagined by humans. if you think of complex games in Europe, at least we usually think about chess. And if you take a chess board, there is 10 up to 50 possible combinations of figures on the board. This is the upper estimates. The actual number is probably a bit smaller, but it's well above 10 up to 40. It's a huge number. Now, if you look at the second number I showed in the slide, 10 up to 80, this is the number of particles in the known universe. And the third number, 10 up to 170, is the number of possible combinations in a Go table. So Go is quite more complex than chess. There is this mind game that I sometimes play with students on the courses on optimization, because we humans, we are not well adapted in understanding how big these numbers are. So I want just to compare 10 up to 80 with 10 up to 170. If you take the number of particles in the known universe, which is about 10 up to 80, and you square it, you get 10 up to 160. What you essentially did is you take the universe and replaced every single particle in it, every electron, every proton, with another universe. So you get a universe of universes. And 10 up to 160 is the number of particles in this multiverse. What you need to do, you need to have 10 up to 10 of these multiverses in order to get the number of possible board game positions in Go. So it's a huge problem. And it was not really believed before 2016 that the computers can actually do this and compete with humans in problems like this. And this was solved by application of reinforcement learning techniques and deep neural networks and similar. But it was really a huge breakthrough. Obviously, reinforcement learning is not used only for playing board games. And in essentially every industry today, you have applications of autonomous agents that are run or governed or controlled by reinforcement learning. In fact, there is a paper written by Lorica in 2017 that tries to summarize applications of reinforcement learning, and he found that essentially it can be applied, and it is applied to almost any business in almost any industry. If we wanted to say what are the key components of applying this technique, Lorica finds that whenever you need to optimize, control, or monitor, you can benefit from using reinforcement learning. And just to highlight one industry, if you take, for example, autonomous driving or generally autonomous vehicles, every major player in the market is using reinforcement learning in order to build their products, including Tesla, Waymo, and others. So finally, let's discuss what is actually the aim of today's talk. I want to present a high-level overview of reinforcement learning. Obviously, there is too little time, so I will only emphasize details that I believe that are of most importance. I want to highlight connection with optimal and adaptive control. And finally, probably at the very last slide, I want to stress some control theoretic considerations which are crucial for safe and responsible application of reinforcement learning in critical applications. This is of great importance for me personally, I think, because I believe that reinforcement learning is a technique that has a great promise, but it is a dangerous technique, and we need to understand how to use it properly. And I believe that the next couple of years and maybe next decade will be highlighted by these kinds of research. So it is, in a way, it is a look ahead, this last slide. So let us start by dissecting a decision problem. So every decision problem has at least two components. There is an agent which acts, and there is an environment which receives those actions. And when we think about the agent and the environment, we must understand that the agent is purposeful. Agent is active. Agent has some agenda. Agent wants to do something. The environment is nothing of this. It is passive. It is reactive. It is aimless. It follows certain laws, but it doesn't have an agenda. So we think of an agent as an active entity and of the environment as a reactive entity. Usually, we have not only one, but many agents that act within the same environment. Those agents may be cooperating, they may be competing, they may be oblivious to one another, but usually there are more than one. And sometimes they may communicate in a way. Probably the most well-known and widely used decision problem is actually classical control problem. In the classical control problem, the environment is a plant. It is the object that we are controlling together with any actuation or sensory devices attached to it. The agent is the controller. The other agent is the user. Essentially, the user is cooperating with the controller. The user is communicating its preferences to the controller and expects the controller to fulfill those preferences by acting on the plant. There are some disturbances coming into the environment, and we may think of those disturbances as coming from other agents. This, of course, is just a point of view, but de facto, a control loop is just a decision loop drawn in a perhaps different way. But it is, in fact, the most utilized decision loop in the world. So let's see what are the topics that we need to understand in order to understand how a decision process functions and how a control loop functions. The main concept that we need to understand is the concept of state and the concept of state feedback. These two concepts are important both for classical control and for reinforcement learning. So we need to come back to our agent and the environment. We have to understand that by acting on the environment, the agent inflicts some change upon it. This is why this is sequential decision problem, because once I perform an action, I have changed the environment, and making the same action again will not have the same result. The environment remembers in a way that what we did to it in the past and reacts in a different way because something has changed. And the state is essentially the response to the question, what has changed? And it was not so easy for mathematicians, for engineers, for scientists generally, to conceptualize this notion of change. And one of the people who managed to do it was Markov. Markov introduced an assumption, which is now called Markov property, that always when there is a change in the environment, we can identify a quantity that changes, and that quantity that changes we call state. So for any environment, we can define a quantity that is called state, and once the agent acts, or once an agent acts, the environment changes by changing its own state, and then based on the change of the state, we have a reaction that is returned in a way to the agent. A state space model is simply a description of the way in which the state changes in response to external stimuli. This is, if you see this little equation in the left, it says x plus is f of xu. X plus is the value of the state in the next time instance, the new value of the state. It simply depends on the current value of the state and the current actions of any possible agent that acts upon the same environment. Obviously, the agent would like to know what is the state of the environment because this is the most effective way to control it. But sometimes the agent doesn't actually know the entire state. It only observes a part of the state. And that observed part in the control theory we call output, but in decision theory it is usually called observation. And we know from control theory that if we know the state, we can essentially control the system very effectively. And so state feedback is a decision policy or control law that tells the agent how to act. So a decision policy is a map that transforms observations received from the environment and possibly data received from other agents into action that is applied to the environment. This is very important because every classical control problem, every reinforcement learning technique will in the end give us a decision policy or a control law that is essentially in state feedback form. And so because state seems to be so important, we may ask ourselves what kind of states there are, what kind of state space model exists. And this is not an easy question. Actually, there are so many of them that probably they deserve a talk on their own. But I would say that there are two main classifications. First classification is based on the manner in which the model interprets time. So if we see time as a continuous flow, we talk about continuous time models. If we see time as just discrete but uniformly spaced events, then we speak about discrete time models. If we only see events but we do not know whether they are evenly spaced or not, then we talk about event-driven model. Of course, there are combinations, the so-called hybrid models or sample data systems, and many others. In reinforcement learning, we are typically focused on discrete time models. This is a bit different from classical control, which likes to work with continuous time models. But classical control works actually with all those kinds of models, yet not all those kinds of models are suitable for reinforcement learning formulation, and we will firmly be in the area of discrete time models. Also, with respect to the data type used to store state values, this hugely changes the complexity of working with environment models. Most reinforcement learning algorithms are initially formulated as working on a finite number of states. So the state can have finite number of values. This is a bit too restricted for real-world applications. So we would like the state to at least be a number, a real number, or a vector of real numbers, or a matrix or a tensor of real numbers, so a collection of real numbers. Sometimes state is an operator. Sometimes it can be a quantity defined on a manifold. Sometimes it could be a function depending on space or some abstract variable. Control theory actually, different types of control theory actually target all these situations. Yet for adaptive optimal control and for reinforcement learning, we are firmly in this area of relatively simple state types. So either we will, in this talk at least, either we will talk about finite number of states, which is the most easy part to explain, or a state that is simply a vector or of real numbers. In reality, most problems can be cast into this form, but sometimes it is not possible. And this discussion is actually beyond this talk. So I will just say this for now. Also, it is worthy to emphasize that all decision problems can actually be classified according to the grid that is shown. So we may ask ourselves how many decision makers are there? And also we may ask ourselves, is the environment static or dynamic? So what actually does it mean to be static or dynamic here? A static environment is one that actually has no states. So it is the environment which does not remember what we did to it before. Dynamic environment is the one that has state, so it has a memory. We are firmly in the area of dynamic environment and one decision maker. This is actually the control field, and this is the classical reinforcement learning field. If we allow for multiple decision makers, then we are talking about multi-agent systems, dynamic game theory, and similar. So for the purpose of this talk, we will assume that there is only one decision maker, and of course, we will assume that the environment is dynamic. So the next completely logical question, okay, environment is dynamic, but are agents also dynamic? Do agents also have state? And the answer is the following one. If the agent is adaptive, if it is learning agent, then it has to have state. It has to have state. To learn is to change. In principle, a change is indistinguishable from learning. However, semantically, when we think of learning, we think of purposeful change. We learn when we change in order to be better. This is why we do not think of the environment as learning, because we consider it to be passive. Environment doesn't want to be better in an abstract way, but the agent has a purpose. It wants to be better in fulfilling its purpose. So the agent is learning when it is changing. But what can change in an agent? The state of an agent can change. So when you have a learning agent, you obviously have a control law, which is state feedback or observation feedback in this case, but you also have an adaptation law. So adaptation law is the manner in which parameters of the agent change in response to the reactions of the environment. And so let us look at this from the perspective of a very simple PID controller. So this is actually the basic control algorithm. It is de facto the driving force behind modern industry. I know it's simple. I know it exists for many tens of years. I mean, probably from the beginning of the 20th century, or even maybe some forms before. But this is the algorithm that ensures that the temperature in the cabin of your car is according to your wishes. It is also ensures that the cruising speed you are using is proper, both in your car and when you're driving in a passenger seat of a plane. It's instrumental in producing beverages you drink, food you eat, and the clothes you wear. It's essentially, it is hidden in plain sight. It's everywhere. So let us look at this algorithm a bit more closely. E is actually the error. It is the difference between what I want and what I get. If I control a temperature of something, the difference between the set point, let's say 25 degrees, and what is actually achieved, let's say 18, this 7 degrees Celsius is the error. So the controller essentially has a state feedback part and disturbance estimation part. PID is so widely used because most environments in industry can be approximated by second-order systems in which state is formulated by a quantity and its derivative. So PID quite insightfully uses this information to emulate state feedback by this first two parts. But the second part is actually disturbance estimation. It assumes that the environment is attacked by a disturbance and that the total disturbance acts in the same way as the control signal does, and tries to estimate this disturbance so to avoid it, so to kill it in a way. And if we look at it this way, then this last part, which I denoted as UI, like integral control, is actually just the internal state of the controller. And also, if you look at the errors, we may know that the errors are not so easy to measure because of the noise. So we need to filter them. So actually, we mustn't control with respect to the errors, but with respect to the filtered errors. And the filtered errors are, again, just some internal variables of the controllers. So both the integral action and the filtered error are the internal state. And the final expression for the control signal is now something that is doesn't have integral inside, doesn't have derivative inside. I mean, explicitly they are there, but you don't see them. It is just a static combination of the measurement and two internal variables, which I am updating every single time step. So the question is this adaptive? So does PID learn? Again, this is a matter of preference. In control theory, PIDs are not known as adaptive controllers. Simply, we don't call them adaptive. Although you can call them that way. It won't change the fact. So let's see what are actual adaptive controllers. An actual adaptive controller has the structure the same as the ordinary controller. Only the difference is that the control algorithm has an explicit adaptation scheme. So there are some parameters that are fixed. These parameters in PID are those gains KP, KE, KD, but there is an adaptation scheme that adjusts the values of these parameters. Essentially, adaptive control is used in situations when the behavior of the controlled object is unknown, or when it changes significantly during the control process. In this regard, adaptive control essentially tackles absolutely the same problem as reinforcement learning. However, it needs significantly smaller quantities of data in order to achieve the control, because it uses system theoretic and control theoretic insights to fix the structure of the controller. So the structure of the control of the adaptive controller is essentially much simpler than the structure of the reinforcement learning controller. And as a prize, we get that we actually can use significantly smaller amounts of data. So also, the adaptive controller is typically trained very quickly, and it is relatively easy to provide theoretical guarantees, at least in simplified scenarios, when will it work better. We should always compare this with reinforcement learning, which does not fix the structure of anything, and as a consequence requires huge amounts of data and significant amount of time to train. It also provides very little theoretical guarantees how will it behave. This is something to which I will return in probably in the very last slide of the presentation. So just as intermezzo, there are many different types of adaptive systems and adaptive control systems. Essentially, we can classify all of them by asking three simple questions. The first one is, what is being learned? Am I learning the environment, or am I learning the decision policy? The second question is, do we adapt and control simultaneously or in stages? So, do I have some setup time in which I measure and adapt and then start controlling? Or I have to control and adapt in the same time? And the final question is, are parameter uncertainty used in control? In most adaptive control systems, the answer is quite firmly no. And when the answer is no, this means that essentially whatever my current estimates are, I assume they are correct and control accordingly. This is called certainty equivalence principle. There is one approach, which is called dual control, which uses uncertainties of the estimates directly during control. Now, quite interestingly, dual control was introduced in 1960s by Alexander Aronovich Feldbaum, who was a Soviet scientist. And the method is profoundly complex, yet it is really intimately related with reinforcement learning. It is essentially an alternative formulation of reinforcement learning without all the computational tricks that are used with reinforcement learning that enable it to be effectively applied today. Essentially, dual control was invented 50 years before its time. And it has all the characteristics that the reinforcement learning has. It simply never had the opportunity to mature. What makes it quite interesting today is that if we merge it with reinforcement learning, we can start asking those important theoretical questions in a setting that is maybe more amenable to give answers to them. And before actually introducing the algorithm, I just want to say that the terminology is not a friend of yours in this field. You saw that reinforcement learning was actually invented as a merging of three or maybe even more completely different lines of research. And each and every of those lines has its own terminology. And in this slide, I just wanted to emphasize the difference in terminology between control theorists and computer scientists. So the rows represent absolutely the same topics. So a controller is an agent. Optimal control is model-based reinforcement learning, and it is the dynamic programming. Direct adaptive control is model-free reinforcement learning, etc. So sometimes it's quite difficult to follow different literature because everybody seems to be using their own terminology. And the good thing is that the situation is a bit better in the last couple of years. It tends to get standardized, so it's going better. Okay, so finally, let us go toward optimal and adaptive decision making. So let us actually introduce reinforcement learning as it is taught today. First of all, we need to visualize the whole decision process as a graph and to see how states, actions, and rewards relate to one another. So we assume that the state space is finite, just for the purpose of this slide. So there are 1, 2, 3, 4 states, and there is also terminal state. So when I am in a certain state, I have options. My options are, for the purpose of this slide, to go by the green or by the reddish route. So every action is represented by the transition, by the edge of the graph. If I choose a certain route, I will get some immediate reward, and I will find myself in another state. Once I find myself in another state, I need to make another action, etc., etc. So this process continues either indefinitely or until I reach some state that I call terminal state. Depending on the type of the decision process, there can be only one, there can be multiple terminal states, or even there are no terminal states. In control, for example, there are no terminal states. Simply the process is going ad infinitum. It's never ending. So the question is, what is the purpose of the decision maker? And this is where actually this is where the great watershed, the great difference between classical and modern control, classical control and reinforcement learning is made. In classical control, we design process, and once we design process, the individual actions come from there. In the optimal control or dynamic programming case, we actually we do not think about process. We think of direct selection of immediate actions and think of the consequences of those actions. So the goal of optimal control agent or a dynamic programming agent is simply to maximize the cumulative gains it receives by making actions one after another. There is a both theoretical and psychological fine point to make, that actually we are typically not interested in maximizing the direct sum, but we also would like to give certain weights to certain rewards. And typically this is done by saying that we like a reward that we will get sooner more than the rewards that we will get in a distant future. And this is taken into account by this gamma factor, which actually it is usually less than 1. So I will weight an immediate reward by gamma up to 0, which is 1. So it has absolute or relative value 1. And then if I get something in 100 time instance, the weight of this would be gamma up to 100, which is something that is significantly less than 1. Of course, there are many problems where it's called a discount factor, by the way, this gamma. And there are many problems where discount factor is not needed, but essentially, let's say it like this. In optimal control and dynamic programming, I'm interested in optimizing the total gain, which is obtained by as a weighted sum of immediate rewards. In order to get actually to reinforcement learning and dual control, I actually need to take one more thing into account. And the fact is that the environment must be seen as not known. So I need to balance between exploitation and exploration, between how much I will exploit what I think I know and how much I will intentionally make bad decisions in order to explore the environment. So these 3 points of view, these 3 different purposes are actually, in my opinion, the main differences between the approaches that are typically classified as classical control or optimal control or reinforcement learning. So it's not actually the problem is the same, but it is the purpose of the decision maker, and these are the assumptions that the decision maker is willing to make. Okay. The most significant quantity that can now be defined, and it's crucial for making decision, is the concept of value of a state. Value of a state is actually the total return or gain that an agent can achieve starting from that state and behaving optimally. So essentially, I would like to find myself into the state with the greatest possible value, because that, in this case, I will get the most of the decision process. And so if I know the state, the question that if I know the value of every state, it's quite easy to make actions. So given, assume that you are in state A, and if I take the green action, I go in state C, and if I go, if I take a reddish action, I go to state B. So what should I do? I must ask myself, what would be the value of state A if I take the green action? Well, its value would be -1 plus discount factor times whatever is the value of state C. So you see, the concept of state brought to us the fact that we need to look only at one step ahead actions. We only need to look into next immediate action in order to optimize the entire process. This is actually one of the great contributions of Bellman, and probably also Isaacs before him. This was actually first derived in continuous time formalism. I won't go into details of this slide, but on the right part is the continuous time Hamilton-Jacobi-Bellman equation. And on the left part is the discrete time counterpart. In modern reinforcement learning, the left part is used exclusively in every single technique. So this is called, in discrete time, this is actually called just Bellman equation. And it has this uniquely, profoundly beautiful property that you make decisions about the entire process by looking only at the immediately next decision. This is huge. This simple fact actually makes reinforcement learning possible. So I don't need to look at all possible combinations 15 steps ahead. Bellman equation tells me that if I know the value of the state, or if I know approximate value of the state, I need to look just one step ahead. Unfortunately, the value of the state is not so good if I don't know the model of the process. Because if I don't know the model of the process, then I can never certainly say in which other state I will go when I apply a certain action, nor can I say what is the reward that I will receive. So in an uncertain environment, instead of values of states, we need to try to find values of actions in states. So a value of an action in a state is just the total return an agent will receive if, starting from that state, it applies that action and then in later action uses the best policy possible. If I somehow know the value of an action in state, then deciding what to do is actually quite simple, because I just have to I know in which state I am. I just find the action with the highest value and I apply that action. And interestingly, Bellman equation can also be reformulated to work directly with action values, with Q values. And so now we are finally ready to introduce the reinforcement learning. So the so-called tabular reinforcement learning is implemented in a way that you actually make a Q table. A Q table is a table containing value for every state in every action. So it can be a dictionary or an array in an implementation of a sort. Then you go like this: you first gather experience, then compute target values for the Q values, then you update the Q table, and then you update the policy. So how do you gather experience? You use actual simulated experience or a combination. You may try to experience just one action, a couple of actions, entire episode, many episodes. This is dependent on the type of the algorithm you use. Then you use you would use either actual returns or you would use individual rewards or a combination to compute targets. You update every single combination of state and action you saw in your experience, and then you update the policy. And then you do it multiple times. So this is a loop. Each time you pass one pass through this loop, your knowledge increases, your policy gets better, and you do it over and over and over. You consume data, and finally, you hopefully you get an optimal policy. Now we come to the technical part, and I will be really super fast. The algorithm for updating Q values is actually the same algorithm that you saw in a PID controller used to filter the error. It's absolutely the same algorithm. This is actually called temporal difference update equation in the reinforcement learning. It's also known as a first order low pass filter in digital control. It's also known as steepest descent rule in gradient optimization. I mean, it's all the same. And depending on what you use for target, you have those many different reinforcement learning techniques, including Monte Carlo in both naive and incremental form. Monte Carlos use episodes to form targets. Then you have these temporal difference methods like Q-learning and SARSA. They use bootstrapping, meaning that they update estimates based on other estimates. And then you have a multi-step SARSA versions, which essentially try to interpolate between SARSA and naive Monte Carlo, or sorry, between SARSA and incremental Monte Carlo, etc. So every single one of these techniques is essentially just the same. The difference is only in what they are considering to be the target. And to come to an end, this is where the deep part comes in deep reinforcement learning. Those tabular methods are okay, but they have a big problem that 10 up to 170 is a huge number. And we cannot possibly store all possible combinations of actions and states in one table. Instead, what you can do is you can build differentiable approximators. And neural networks have proven to be quite extraordinary differentiable approximators. And instead of these tables, we can use networks. And when we use networks, actually the state of the agent are the parameters of the network. And when we update the state of the agent, we are essentially updating the parameters of the network. So we are training the network. And we can do this online. And this online training is something that differentiates deep reinforcement learning from other types of deep learning, like from the supervised or even unsupervised learning, is that actually you are required to do this in online fashion. And there are many things from adaptive control that can help us here to avoid problems like forgetting, like training and stability, and similar. But what is also important that when we introduce approximators, we also do not need to have a finite state. finite number of states. We can work with continuous states because we don't need. So essentially, we can work with an infinite number of states because we don't need to encode every possible state action combination into memory. Okay, the number of parameters in modern network is huge. We are talking about tens and hundreds of millions and more, but this is manageable. This is still countlessly time less than 10 up to 170. And so to finish the presentation, I just want to return to the first thing I said, maybe on the very first slide. What I personally, as an engineer, am interested in reliability. And reliability actually comes if I achieve the following four things: interpretability, safety, robustness, and stability. Every single one of these topics is well understood in a control theoretic world or control engineering world, and they are necessities if you want to apply intelligent agents in critical systems. So this is something that I expect will be a topic of my personal scientific and technical interest in the years to come. So I want to thank you for your kind attention, and if you have any questions, you can of course now ask them in Q&A part, but also you can send me directly email, or even if you are in Novi Sad, you can come and we can have a nice offline talk in the office. Thank you so much.
Thank you so much, Professor.
Thank you, Milan. Thank you, Milan, very much. So do we have questions? Or
yes, can I ask a question?
Yes, of course.
Based on your explanation, Professor, if you want to use the Q learning in order to find the solution for a problem, we can benefit from the Q table, okay?
Yep.
Okay, in this case, can we reuse the data actually will be achieved by training process?
Yes, yes. Actually, this is the way how you do it. Only in toy examples you actually put an empty table in production and start learning. The reason is that by definition, reinforcement learning agent will try to do everything, even completely stupid or dangerous or unlawful things. If you would put an empty table and try to train an autonomous vehicle, at some point the vehicle will try to see what will happen if it kills a pedestrian. So you need to have constraints that are hard. Pedestrian is a hard constraint, but also you need to allow the agent to do dangerous things in a simulated environment and to make sure they are bad before letting it retrain itself in an actual physical environment. And through all these processes, you simply keep the old Q table and just update the entries, or keep the old network and just retrain it. So, but you typically do not put an empty table or an empty network in production. Okay.
Okay, but my I didn't get your point. But my question is that can we reuse the, for example, train data from the previous training process? For example, you can imagine we have a map, actually a city map. We want to find the shortest path between A and B point. Okay.
Okay.
After that, we actually train our Q learning algorithm.
Okay.
We receive the result. The result is very well, okay? But we want to reuse the train actually data in order to find the different optional, for example, position, for example, C and D, okay? Is it possible to reuse the train data from the previous training process in Q learning algorithm?
Oh, okay, yes, it is possible, but in this concrete case, it also depends on how much does the map changes between two applications.
No,
because
it's same. It's same.
It's the same.
Same. Actually, the same map, city map.
Yeah, it should be possible. Even if it is the same map, it could happen that in the first case, you are passing through areas that have certain properties, and that in the second case, you are exploring another part of the map that is very different. And so in this case, your initial agent will perform relatively badly in the new area of the map, but it should be able to learn more quickly than an empty agent. So yes, it is possible, definitely.
And also, if you reuse that train actually data, the result will not be optimum. Yes?
No, it will not be optimal. Yes.
Okay, thank you so much. Thank you so much.
Yeah, thank you.
So if there is no additional questions, we can conclude. Well, bravo, Milan. Thanks again for your lecture. And so if you have questions, please contact us directly through the link or you directly Professor Pajic on email. So have a nice day. See you on next talk. Bye.
Thank you so much.
Thank you very much.
Thank you.
Great presentation. Thank you so much.